Shown in the figure below is a system of blocks connected by a massless string running over a massless pulley. The coefficient of friction on the ramp is mu k equals 0.1. The 8 kilogram block is sliding down the ramp. Find all of the following. This is a classic example of a force problem. In a force problem, we actually don't care what we're asked in the problem. Instead, what we do is we analyze the problem by the appropriate steps every time. The first step in every force problem is draw a free body diagram. I'm going to begin with the 2 kilogram block because this will be giving us a one-dimensional free body diagram. Just by the look of it, the 8 kilogram block will be giving us a two-dimensional free body diagram, and so we'll get 3 equations, and we expect in the end we'll get 3 unknowns. This red dot will represent the 2 kilogram mass, and we need to begin by naming any one force acting on the 2 kilogram mass. The first one I'll mention is mass times gravity, where the mass is 2 kilograms, so that's 2g downward. Tension upward, because it's tied to a string. The 2 kilogram mass does not touch a surface, so it has no contact forces, and that's it. That's every force acting on the 2 kilogram mass. The next step, after we've accounted for all forces, is to draw the coordinate system, and the principle by which we align the coordinate system is with the acceleration. In this problem, it's already been stated that the 8 kilogram block is traveling down the ramp, meaning that the 2 kilogram block is moving upward. For that reason, we're going to select the positive direction to be upward on the 2 kilogram block. And this will yield us a single equation. The y equation for the 2 kilogram block is tension in the plus direction, 2g in the minus direction. That's the sum of all forces. The sum of all forces is m times a, and indeed the 2 kilogram block is accelerating. Since this expression has 2 unknowns, we place a box around it and save it for later. What we have not done yet is analyze the 8 kilogram block. I'll highlight the 8 kilogram block in blue and begin with the first step in every force problem, which is to draw a free body diagram. This dot will represent the 8 kilogram block. Naming each and every force, the first one we recognize is gravity, which will be pointed downward. Gravity is of amount m times g, and the mass is 8. The next thing we notice is that the 8 kilogram block is in contact with the surface of the ramp. Contact forces come in 2 types. First is the component perpendicular to the surface, where we use the mathematician's name for perpendicular, which is called normal. Every surface provides a normal force. Sometimes the surface will also apply a force parallel to it. In that case, we would have friction. Here we do have friction because mu k is 0.1, and so we draw the frictional force in the direction so as to oppose sliding. Since the 8 kilogram block slides down the ramp, the frictional force will be parallel to the ramp, upwards of an amount mu k, which is 0.1 times the normal force. Finally, we have one more force to account for. The 8 kilogram block is tied to a string, and strings always pull. So in addition to the frictional force, there will be a tension force up the ramp. Now that we've named all the forces in the problem, the next step is to align the coordinate system, and as always with every free body diagram, we align the coordinate system with the acceleration. What we notice about the 8 kilogram block is that it is sliding down the ramp, and so we will set the plus direction for our coordinate system with the acceleration, which is down the ramp. A two-dimensional free body diagram requires 2 coordinates, and the second coordinate should be perpendicular to the first. That nearly completes our free body diagram. What we see is that The frictional force, the normal force, and the tension all lie nicely along the coordinate system, and so will occur in one and only one of the two force equations resulting from this diagram. However, the gravity force does not lie nicely along the coordinate system, and therefore we need to break it into components. The manner in which we do that is we begin at the tail of the vector, and we follow one of the coordinates. I'm following the y-axis, and we do so until completing the triangle is done with a piece parallel to the x-axis. These yield the two components of gravity that will appear in our equations, and what we need to do is we need to decide where in this triangle the 30-degree angle from the ramp goes. Looking carefully at the ramp, we notice that the ramp forms a 30-degree angle with respect to the horizontal. In our free body diagram, we certainly have a line parallel to the ramp. That line is the x-axis. However, at the current time, we don't have a line in our free body diagram, which is horizontal. So what we'll simply do is add a horizontal line to our diagram, and as a result, we can identify very easily where the 30-degree angle is. The 30-degree angle is between the ramp and the horizontal. If that angle is 30, this angle is 60, and if that angle is 60, this angle must be 30. At this point, we can easily label our two coordinates of interest. The side that is opposite to the 30-degree angle will be 8g times the sine of 30. And the side that is adjacent to the 30-degree angle will be 8g times the cosine of 30. Meaning that in one coordinate equation, 8g sine will appear, and in the other one, 8g cosine will appear. To write our equations, I'm going to begin with the vertical direction, or in other words, the one along with the normal force. We'll call that y. We don't have a preference for what should be the plus direction in this coordinate because there isn't an acceleration along the y-coordinate. So taking the most natural choice, we will make n in the plus direction, meaning that the 8g cos 30 is in the minus direction. The sum of all forces is ma. However, the acceleration in the y direction is 0. Looking at this equation carefully, we notice that it has only one unknown. That unknown is the normal force, and so we're able to solve that the normal force is 8g cos 30, which turns out to be 67.9 newtons. Finally, we have one more thing to take from our free body diagrams. We must analyze the horizontal, or quote, x coordinate from the diagram for the 8 kilogram mass. We've already selected down the ramp as the plus direction, making the 8g sine 30 the only component of force in the plus direction. This then yields our x equation, 8g sine 30, minus the friction, which is mu k times the normal force, minus the tension, equals sum of the forces is m times a, the mass of this object is 8, and the acceleration we don't yet know. This makes our second equation into unknowns. To solve the system, we need to take the two equations in boxes, write them next to each other, and then finish the algebra. Now that we've collected these two equations together, we investigate the principle of the tension. We know that tensions always pull, and therefore, if we have been consistent with our coordinate system, the tension should appear once with a plus sign, which it does in the second equation, and once with a minus sign, as it does in the first. When that's true, we not only have correct equations, we have very simple algebra to solve them. We simply sum the equations themselves, causing the tensions to cancel, yielding us 8g sine 30 minus 0.1 times the normal force, that's going to be 6.79, minus 2g, equals 8 plus 2 is 10 times the acceleration. So that the acceleration is equal to 1.28 meter per second squared. Now that we've solved our two simultaneous equations for one of the two unknowns, the acceleration, we simply need to plug this acceleration back into either of the two equations. I'd like to choose the simpler of the two equations and solve for the final unknown. This will yield tension minus 2g is twice the acceleration of 1.28, or the tension is equal to 22.16 newtons.